Welcome everyone to our webinar, Building Trust in Embedded Systems. We give you an introduction about what is important when using QNX on Phytec hardware, what are the advantages and disadvantages. First of all, as you can see, hopefully you can see my slides. I'm not Ralph, but I'm Christian, so you have to trust me that I'm doing this right. Ralph was sick, so I have to be the replacement today. Hopefully it will be still entertaining and a good seminar for you. Phytec is the host for this, but nevertheless, first I would like to hand over to Albrecht Ullmann from BitCtrl to give you a short introduction and what to expect today from this webinar. So Albrecht.
Thank you, Christian. Welcome also from my side to this webinar together with Phytec and QNX. We have 4 topics that we would like to talk to you about. First one is an introduction where I will talk about some important trends that we have seen in the embedded space and that seem important to us and what solutions we offer to handle these. Then I will hand over to Christian, who will talk a little bit about the Phytec hardware. After that, Sachin from BlackBerry QNX will talk about the QNX OS solution. And in chapter 4, it will be back to me again, and I will talk a little bit about the system integration challenges that you are facing in today's embedded systems world. Now let's start with some trends that we believe are important. So what we are seeing is there is an increasing demand for compute power, and that is driven very much by AI-based algorithms that either when they run on the CPU need brute power, or if they are using on designated hardware like GPUs or NPUs, they need a high level of software adaptation to really make use of it. But also an increasing customer expectations with regards to functionality or usability and user experience or integration of third-party software drive this demand. At the same time, we are seeing that the hardware manufacturers are integrating ever more functions on a single piece of hardware, and we have an increased consolidation of hardware platforms. Now, this is great because it reduces the complexity of the hardware design, but it just moves the complexity to the software because the software now needs to seamlessly adapt to these complex SoCs. Additionally, we have an increasing regulatory compliance and certification requirements. So there is, first of all, functional safety regulations in automotive, in industrial, in medical, and in other industries. And additionally, there is additional cybersecurity and product lifecycle regulations that need to be taken care of. And very new, you probably all have read about the EU AI Act. We have now additionally AI-related regulations coming in. Now, what does this mean for the technical side of things? These complex SoCs now span multiple timing domains. So there is the hard real-time domain, which is, for instance, for fast communications in the sub-millisecond range. But there's also a soft real-time domain for applications that work in the order of up to a few seconds. But also there are long-term functions running on these devices that accumulate data potentially over years and need to take care of. And all this is being run at the same SoC. SoCs now also span multiple domains of criticality. So there is a safety-relevant domain where, let's say, the control application for industrial or medical equipment is running. Also, the HMI, at least in parts, is often part of the safety critical path. But there are also non-safety relevant functions that are executed at the same SoC, for instance, auxiliary processing, cloud connectivity, etc. And both domains need to be isolated from each other on this SoC, but still securely exchange information in order to make the system fulfill the intended function. And this unfortunately leads to a higher integration, testing, and certification efforts. So the testing and validation effort grows exponentially with system complexity, and particularly in the AI space, some algorithms cannot be fully tested anymore, so different strategies are necessary. What can you do to meet these trends? And more importantly, is there a way to turn what looks like an additional burden into a competitive advantage? As a hardware supplier, you need to know these challenges, which means you need to supply a system on modules with the latest SoCs, board bring-up support, and all this backed by the SoC manufacturer itself. You also need to make sure that you scale the application by supplying a range of modules with different properties, which can be interchanged easily. And you need to offer your customers a long-term product support and replacement strategy, because lifetimes of 10, 15, or even more years are the norm rather than anything else. As operating system supplier, you need to know the importance of this very critical component. So the operating system must be able to fully isolate tasks, both in time and space, depending on their domain. The OS must be hard real-time capable to meet the timing requirements. OS must allow integration of third-party software and tools by adhering to industry standards. And last, the OS must also support the customer's certification case. For the system integrators, they need to be aware of and experienced with system complexity. So ideally, they have an own development experience, and they are able to utilize preset platforms and off-the-shelf components to build the system in time and with reasonable risk. And of course, they should have a team with deep experience in integrating products and technologies of very different kinds. Now, luckily, we have one of each here in our webinar. So Phytec will be talking about the hardware, BlackBerry QNX as OS supplier, and BitCtrl as system integrator are here to tell you about these trends and how they are managed. With this introduction, I will now give back to Christian from Phytec.
So thank you, Albrecht, for the introduction. I switch to my slides again so that we can continue with the presentation. As Albrecht said, we at Phytec are all about hardware. We create hardware for customers and we make sure that it really runs to the standards you expect from us. Why since Phytec is a company, it's a global company located in Mainz, Germany, with our production facilities also in Mainz, Germany. So it's made in Germany, but of course we utilize a worldwide distribution network. We have several offices, as you can see here, worldwide located. Our employees make sure that we have global support, global development, and that you can trust in the development we do for you. What do we do? Basically, it's embedded hardware. We are the embedded hardware specialists you need when creating a product from scratch or when you're integrating something into your own system. So in the middle, you see the Phi cores. This is really the core of our system. So as Albrecht said, we integrate the chips, the technology from the chip suppliers like NXP, ST, TI, whatever, onto the systems and help you to integrate them onto our Phi boards or your boards, basically your design, and enrich them with technology like vision. You can see here the Phi cams, but also AI technologies or other emerging and relevant stuff. We do not stop here, so you can also step a little bit further, take the OEM products, enhance them with the software side. Normally, we focus at Phytec on Linux software. Today, of course, we will show you how to use Phytec hardware together with QNX operating systems. Basically, what I said before is what we are doing at Phytec is we partner up with companies like BitCtrl, BlackBerry QNX, other partners to bring you the experience you need on your custom hardware to fulfill the product needs you want in the field reliably. When I'm talking about the matching hardware for your product, we normally start at the SOM. So this is really the core of your product. Today, I present you the i.MX 8M Plus. It's a core from NXP. Albrecht introduced you already to the AI side of industrial technology, which is presented here with a NPU on the chip. We make sure that it will work perfectly with your hardware, your interfaces, your industrial networks you build around the Phi core. Of course, we do not stop at hardware development. So our core business is the SOM, the integration of the processor to make it easy for you to start your project or to get your project into the market. We start with diagrams, do all the calculations you need, go over to a BOM, which is crucial to be reliable and trusted in this market, because sometimes, as you maybe remember from the Corona crisis, parts are going out of stock. You have to replace them. This is all managed by Phytec's services. So we are doing the complete service with handling and production. Production, as I said, in Mainz, in Germany. So you can be sure that it's not, you can be sure that it's up to the standard you need. Very important, of course, in this session is the trust, the security. So we are very proud of doing all the key handling for our customers in a specific protected area. So you can be absolutely sure that the keys you provide us with are only handled by the people necessary to handle them. Additionally, we do all the certifications you need for the different vertical markets, like medical certifications or, for example, the automotive certifications you need. We handle this with partners or by ourselves. And for the software part, normally we stop at the login prompt. This is our business, and then continue to supply you with good partners like BitCtrl, QNX, or other partners to enhance the hardware we produce for you with the software you need to get your process or your product up and running. For today, we prepared a special QNX 8M Plus kit. So we have a combination for you if you're interested in, which is a full QNX installation running on our certified hardware. So you will get all the information afterwards on how to get this kit, how to try QNX on one of Phytec's board. That's it for me. Thank you for listening. And I'll hand over to Sachin from QNX to give you more specific information about why QNX is the right choice to run it on Phytec's products or in general. Thank you.
So thank you, Christian. So let me share my screen. All right. So good day, everyone. I'm Sachin Saran, manager of the field application engineering team here at QNX in EMEA. Our team are technical influencers who looks after the general embedded market that covers almost everything which is non-automotive. So today I will brief you on QNX foundational products and our safety and security story. So hopefully by the end of the talk, you would see why and how you can benefit from QNX in your products. Just to make sure that you guys can actually see my screen properly. So QNX is part of the BlackBerry organization, hence why you hear, BlackBerry QNX. And within BlackBerry, you have two key business units, the cybersecurity and IoT. And I will not be talking about our cyber side of the business today, but focusing on primarily QNX in our IoT business unit. So within this division, we have multiple product lines, including the QNX real-time operating system, the hypervisor, both being safety certified, and which we will present in the next few slides. And that's the foundation for the development of reliable, scalable, safe, and secure embedded system. So QNX is already embedded in millions of devices around the world. Our products confidently support many mission-critical devices in various industry verticals. Of course, most prominently in transportation with cars, trucks, rail, and even heavy machinery. But also in medical devices such as surgical robots or laser eye surgery machine and MRI machine, for example. But you can also find QNX in the industrial robotic market. Things like gas and wind turbine controllers, nuclear power plant controllers, industrial PLCs, but also industrial robots and AMRs, just to name a few. So QNX is truly a global organization with sales team across the world, but also engineering resources, what you can see on the slides here. So our engineering team, whether it is product development or services, they are kind of strategically located in time zones where we can support our customers efficiently and on site when required. And we are able to service all these markets with our broad safety certified portfolio of products. A proven real-time microkernel that has been used for decades in mission critical systems. But that also comes with broad set of security features to help secure and harden your system. So not only providing you with a solution that is reliable, safe, and secure, but also allows you to scale across product lines. So with 40 years of innovation and thousands of man-hours of experience, we are trusted by our customers to deliver on our commitments with a 100% SOP success rate, but also long-term customers. And that success is driven by 5 pillars. So safety, where you can focus on certifying only the parts of the system that you build, not the OS. And you can also allow to build mixed criticality systems thanks to the architecture of QNX. But we also have a comprehensive set of security features that can help you secure your system as well. And with our hard real-time capabilities and the ability to scale through multiple systems from a performance point of view, so customers can be confident that they will have a highly efficient and performing product. But a safe system needs to be reliable as well. We've deployed in millions of safety critical systems, so without failures, and that is backed up by our proven in-use data. And the same OS can be used across safe and non-safe systems. And you can have a modular platform strategy that allows you to scale your products across business needs or requirements from your customers or even changes in the market. So now let's dig into what makes QNX different and why it might matter to you. So if you look at QNX, and an OS you might have had some experience with, like Linux, for example. So from a developer's perspective, it is a lot like Linux. It is built from the ground up to be fully POSIX compliant. So if you develop code under Linux, you're going to find it relatively easy to port over to QNX. But unlike Linux, QNX RTOS was designed to be a real-time, fully deterministic operating system. The QNX RTOS is a microkernel. So here on the left, we represent QNX, and on the right is Linux, which is based on a monolithic kernel architecture. But really, it could represent any OS or RTOS for that matter with a monolithic kernel. So although QNX is Unix-like, but as you can see here, it is very different. So in a monolithic kernel, everything from basic OS services to device drivers to protocol stacks, they're all contained in the kernel, all running in one big kernel address space, running at highest CPU privilege level. So consider the implication of that in a monolithic kernel. So if one of those components fail, the entire system may become unresponsive or even crash. So with QNX, the microkernel is designed to contain only the fewest possible components with unrestricted CPU privileges. And that boils down to things like CPU scheduling or memory management or interprocess communications and so on. Everything else is implemented outside the kernel space in its own protected address space, whether it's your drivers, your stacks, your applications, everything. But also, every software component in the QNX world is a process. And those processes, they are isolated, they are firewalled from each other, so they cannot impact each other. So if you happen to have a fault in one of those components, it is contained within that component. It doesn't have that level of privilege necessary to affect any other component. So as you can see, this is inherently safer and arguably more secure design than a monolithic kernel. But the OS architecture should also support development of an intellectual property library that can be reused across product portfolio and across generations of products. It must allow code for drivers and applications to be easily added or updated without requiring the addition of new items or a kernel rebuild. So with those characteristics, software designers can develop once and share common low-level driver software components like file systems or user interfaces, or even standard device drivers such as USB across products. So this ability to share or reuse components speeds the introduction of new technologies or out-of-the-box components in as many products as possible, as quickly and efficiently as possible. And something that we've seen too often, those valuable resources are focused on OS and driver maintenance, which provides no added or competitive value, but it's complex enough to require senior level resources. So a microkernel like QNX separates file systems and the multimedia and the network stacks so that they run in user space. So this means that the microkernel OS really needs to be recompiled, and component integration can be done once and reused across multiple products. So this separation enables the critical innovations of modularity and scalability. So you can easily reuse custom code or drivers or bring up new hardware or add off-the-shelf third-party components to all your products quickly and add value for your customers. So now let's look at safety. And functional safety is at the core of what we do at QNX. It's now our DNA. We have been helping streamlining safety certification for well over a decade. Our involvement with functional safety standards started more than 10 years ago when we released a QNX safe kernel, which was certified to IE 62158. And we've since released several certified versions of our QNX operating system under the brand name of QNX OS for safety. So with the addition of certification for ISO 26262 for automotive and IE 62304 for medical, and we've always done so to the highest safety integrity levels. And as you can see from this slide, we are constantly expanding the certified scope of our safety products, going from the microkernel, the C library, the C++ library, and more recently, the MATS and SMMU support for busmaster caging. And a few years ago, we introduced QNX Hypervisor for safety, but also add-ons such as QNX Black Channel Communication technology for safe communication between interfaces between different nodes. And just last week, we released a QNX file system for safety. And at the same time that we've been expanding the scope of those products, we've increased our ability to deliver functional safety services as well, from training to audits to workshops, all of this to help customers achieve their safety goals. When we talk about safety, spatial separation is arguably the most important aspect. So as I mentioned earlier, the code that you develop will end up as a process in QNX, protected from others are protected from it. And this is done by using the memory management unit, which is supported by most of the latest ARM and x86 processors. So everything is encapsulated using the MMU. And every process has its own virtual address space created by the MMU. So if a process tries to access memory that it does not own, an exception will be triggered. But of course, inside a process, you can have one or more threads running the same virtual address space. So each thread stack will use the MMU to provide guard pages to protect from stack overflow. And also very important is temporal separation. And that's important when we talk about QNX being real-time and deterministic operating system. So time-critical, safety-critical aspects of all components behave deterministically in your system. Threads that you would define as more critical will not be slowed down by the threads that you define as less critical, all based on the priority that you give them. And you're going to have threads with the same priority levels. You can choose different staging algorithms if that's the case, whether it's FIFO or round robin or sporadic. And these algorithms are used on a thread level, not system-wide. So that gives you more flexibility on how you design your system. And then you have the concept of busmaster caging. So you have devices with system MMUs, and QNX can use those SMMU to prevent DMA devices, such as network cards or graphics cards, for example, from accessing memory outside the defined boundaries. So protecting against DMA IO device from writing to memory outside its defined scope. And then finally, we have the hypervisor solution that enables you to have strict isolation between safe and non-safe guest OSs, while enabling you to add more functionalities to your product and enable consolidation of platforms as well. But you cannot achieve safety without security. And QNX, we provide a comprehensive system approach to security that builds on OS features. And that system approach incorporates industry standards such as chain of trust, integrity management, and mandatory access control. And where it makes sense, you have a security configuration that is described in a central policy repository to allow system architects and integrators to specify, to review, to implement security policies. And security is achieved by using different optional security mechanisms, some of which you can see on the slide here. You have ASLR, for example, which makes it harder for an attacker to guess where the code is loaded in memory. ASLR varies the location of data and instructions each time an executable is loaded. And control over a process ability to perform any action is governed not by the user ID of the process, but by a set of approximately 70 permissions called process manager abilities. And use of abilities allow the privileges afforded to a process to be tailored to its needs rather than being all or nothing. So allowing you to build a rootless configuration system. Or you can use encrypted file system to prevent an attacker from seeing or modifying sensitive data. And there's a lot more. Each feature adds a different layer of security and serves a different purpose. And we have a comprehensive guide and training as well to help you implement your security strategy in your products. Now, the power of compute platforms has increased in the embedded domain. Designers have the luxury to add more functions on each SoC. These functions can be different and combine safety-critical and non-safety-critical processes. The challenge is to isolate these functional domains such that they do not impact each other negatively. And for this, we have a powerful but yet flexible hypervisor. We know that IT infrastructure has been using hypervisor for a very long time. So what you see on the left here is a full hardware virtualization, which is common practice in cloud infrastructures or desktop as in VDI, for example. And then you have the other extreme, what you see on the right, a type 1 hypervisor or bare metal. It runs directly on the host hardware to control the hardware and to manage guest operating systems. So QNX hypervisor provides flexibility in the blend of virtual machine and host environments. So it can scale from that small and efficient hypervisor that supports multiple isolated guests. So it basically acts as a separation kernel. It boots up, launches a virtual machine, and that's the only thing it does. Or you can extend to the selective sharing of devices to virtualize Linux and Android systems, for example, using standards like VirtIO, where you're just sharing what you wish to share between your different operating systems. Or you can go all the way up to a full-featured hypervisor environment, or a type 2, which is OS-assisted hypervisor, where you can have support for advanced sharing frameworks like graphics, audio, touchscreens. But you have key services running in the hypervisor host as well. So the QNX hypervisor has a type 1 architecture, but it can scale all the way to a type 2 design, or somewhere in between, which is actually the most common use case we see in the embedded domain. So when you look at this slide, on the left is the QNX RTOS. So MMU protected memory space for spatial separation, priority-based, real-time scheduling, SMP support, and all these security features. What we have done is we've added an extension, a virtualization extension to the microkernel. So now it becomes a hypervisor that schedules and isolates whole operating systems. And that's been built by the same QNX team that designed and built the safety microkernel. So the programs that you build initially for that QNX operating system on the left will work exactly the same if you have a hypervisor-enabled system like the one on the right. And we purposefully put only things in that kernel that requires at the highest privilege levels to support a virtual machine. Everything else we put into a virtual machine manager, which can fail while the rest of the system can continue to operate. So you have this new kind of process called QVM, QNX Virtual Machine Manager, and you can have multiple of them. So emphasis here on the word process. As you've learned, processors are isolated, firewall from each other in QNX. So it does all the main work, such as setting up the memory, setting up the virtual CPUs for the guest OS, create and destroy memory regions, set up the pass-through devices, even set up the virtual interfaces, including the VirtIO or scheduling policy. And inside those processors, you can run your guest operating system. So beyond from isolating processors from each other from a time and memory perspective, the hypervisor can also isolate full operating system from each other. So some of the benefits of this design is that you can run with no or small guest OS changes. You can take the latest Android versions or Linux or latest Ubuntu Linux, use the drivers that are supported by these guest OSs, put them in a virtual machine, and they would run almost correctly. You don't need to have a service OS or a domain 0 to support the guest, which reduces complexity without sacrificing on safety and security. And we also support the VirtIO standard, which is maintained by the Oasis Foundation, allowing for a much easier integration and updates for your Linux and Android guest, but also allows you to decouple yourself from the SoC. It also inherits the security features, the POSIX runtime environment, the unit regression testing of the existing QNX microkernel. And when we introduce a new feature in the microkernel, the hypervisor also benefits. And we know that as part of your platform strategy, you'll need to leverage and access open source software. Porting any open source software to QNX is relatively easy since we are POSIX compliant. In most cases, it's simply a download and compile exercise. In fact, we ship a lot of open source components as part of our QNX software development platform. Our tool chain is based on GCC 12.2. Our C++ library is now derived from LLVM16. Our network stack is based on a FreeBSD implementation. But we've also ported things like ROS over to QNX and TensorFlow, or even GTK for a simple UI. So open source is a double-edged sword. At BlackBerry QNX, we are well aware of the potential pitfalls of using open source, but we have expertise in-house to help your team successfully incorporate open source as part of your platform strategy. But also, as part of our own QNX long-term strategy, we're going to be doing more of this and upstreaming them to GitLab as well as GitHub. So I'll put a couple of links over here on the slide where you can go and have a look at what we've already been doing for the past few years as an open source porting. So as you've seen, QNX is much more than simply the OS and tools. You've heard about our safety story, our security features, hypervisor, but there's more. We have our own professional services team here to help with architecture and porting assessments. They can assess and make recommendations to help you get your ideas or your products from where they are today to where they need to be. But we also cannot achieve our customers' goals without our partner support. So there's a large ecosystem of platforms, products, services, and they're all available to help you realize your designs and goals. We work closely with silicon vendors and board manufacturers like Phytec here, for example, today. But we also have a large ecosystem of partners, distributors, and value-added integrators, providing additional middleware products, hardware support, and other services for QNX. And you will hear from BitCtrl right after me and know more about what they can provide to you. So before I end and pass the baton over to Albrecht, I'd just like to share a couple of links which are public, where you can find more information about QNX. You can have access to our user guides, which goes into more details on the architecture, but also talk about the security features and how you can implement them. And finally, you can also request a free 30-day trial of our QNX real-time operating system through the link you have here on the slide. So thank you for your time, and I will now pass you on to Albrecht to the next session. Thank you.
Thank you, Sachin. It's now back to me again. Right, about our company, BitCtrl Systems, we are based in Leipzig, in the eastern part of Germany, but operate worldwide. We are a small company, as you can see, but we've been around for quite some time and have also done a fair number of projects and a fair number of customers that we have been working with. And we have several segments where we operate. Mostly it's the industry sector of embedded systems, traffic telematics, and also infotainment and inclusion solutions for public transportation. Now, in the field of embedded systems, we've been working with Phytec for more than 20 years and with QNX since BitCtrl's foundation back in 1990. Now, first of all, I would like to talk a little bit about the development models that we found most useful. So at the left side, there is the most extreme model, which I would call totally developed on your own. It basically means you write every line of code yourself. That's good for large volumes and meet hard constraints, and it's well established in automotive and medical, but it's the most expensive solution both into development but also into maintenance. The other extreme would be to just use pre-built automation platforms that offer you scripting and declarative and other no-code approaches. And that's good for small volumes and has the problem that the customization that you can achieve is limited because usually you do not have access to the operating system itself. But it's well established in the industrial space. Now, what we've been doing is a little bit in between. So we are using pre-built components and integrate them together with purpose-built software. That's good for medium volumes, but it can scale to high volumes as well. And it allows you to get started quickly with a solid and field-proven architecture and then build your system from there. And in contrast to this right-hand side example, it does allow you access to the operating system, and therefore it does not limit your ability to customize the system. And it also addresses to build product variants easily and also to address retrofit scenarios, which we find quite important because a lot of investments which are done nowadays are replacement investments that have their own specifics that I'm going to talk about later. This is the approach that we are taking when we build systems. And how do we achieve this? So first of all, we develop and maintain an own product line that act as the foundation for the products that we do. And these products, they are used both by our customers and ourselves. I will introduce one of those products at the next slide. And of course, we know and integrate a selected third-party products and maintain tight relationships with their manufacturers. And that enables us to build functions into the system that we cannot develop ourselves. And the focus here really is on selected. So we have not too big, but very established relationships with third-party suppliers. And we have a team of software engineers that understand the use case of the customers and then build the business logic by combining our own and third-party products and purpose-built code in an optimal way. Now let us talk about one of these foundation products that I've been talking about. One of those is called Flex Control. It's an embedded SCADA software solution which can act as a real-time automation platform in an embedded system. It comprises two parts. One is what they call the project engineering system, and that is used to define the project. It's defining a set of what we call process variables, and in their entirety, these data objects describe all the data points of the system. The counterpart is the runtime system with what we call the real-time database. And that will make those process variables go live when the system starts up and enables the clients to interact with them. So there are some generic clients like the historian or an alarm database, and of course, logging and monitoring tools that we supply as part of the package. There's also a set of standard drivers for connectivity to enable external communications like the EtherCAT or Modbus, just to name a few. And the good thing is that there can also be developed specialized drivers, even on specific customer hardware that can be plugged in very easily, as I will show on the next slide. All the clients use what we call a Flex Control toolkit to talk to the real-time database in the same unified way. In addition to that, Flex Control implements a subset of IEC 61131 language, and that allows customers to code algorithms and functions. And the text that we had on the previous slide is now here given as a picture. You see the Flex Control core in the middle. It is sitting on top, the QNX real-time OS, which in turn is running on the hardware from Phytec in this case. At the left-hand side, we have the communications, and we have actually shown here that we have both very modern and recent, like EtherCAT communication, but we also support serial or Profibus communications to connect to legacy equipment, as I will show at the next slide. At the right-hand side are standard protocols that allow you to connect to the cloud world. And here you can see the possibility that customers can write a native app which is running directly against Flex Control. Now, in order to illustrate it a bit, I have prepared an example usage scenario. Let's say we want to connect a heterogeneous installed base to a central system. At the left-hand side, you can see an existing equipment, which might be very modern state-of-the-art equipment, right down to legacy systems that don't have any type of security or standardization on board. Examples for this setup might be the machinery park in a factory shop floor, medical devices in a hospital, or some control equipment in an energy distribution substation. At the right-hand side, we have this famous new world in the cloud with lots of central systems that accumulate data. They can be on-premise, like the control room, SCADA, MES, or ERP, but they can even be based in the cloud. And the goal here really is to connect these two worlds seamlessly, securely, and most importantly, bidirectional. And that presents some challenges. So first of all, in most cases, there is no simple one-to-one mapping between these two worlds. So there must be a brain in the middle which translates without losing information. And the second thing is, connecting from the left side to the right is usually not so much of a problem. However, transferring data securely from the cloud down to a shop factory floor is usually a much bigger problem, particularly in terms of security. Now, how can we tackle this problem? So first of all, we put a Flex Control instance in the middle, and we select the most important features like a real-time database with ring buffers, some built-in functions like averaging, and also alarms that can even have multiple thresholds. Then we connect the existing equipment, and by way of example, I have shown here a generic connection which comes as part of the package like EtherCAT, but it can be also a proprietary solution that connects even to custom hardware boards. Likewise, at the right side, we can connect to the central system either using generic ways, SQL as the most simple example, but also here we can implement proprietary protocols that connect to a central system, let's say via HTTPS. This is already the real-time data path that you can achieve with Flex Control. But what else can we do? let's say we can use the history module. The use case here would be that we buffer some values and events for submission after a connection loss. The connection to a central system, even it's on-premise or if it's in the cloud, can get lost for seconds, minutes, or even days. But with the history, all the accumulated data can be transmitted when the connection comes back. And so the archives here in the central system are always complete. Another possibility would to add a FX program. We call it functional extension. And the use case here would be to describe some simple mappings to transfer data from the left to the right and from the right to the left side. And now a really interesting possibility is depicted in the middle. You could code a custom algorithm which may even contain third-party libraries that you might not even have the source code for. And this is possible with the Flex Control Toolkit. It allows you to safely integrate third-party C or C++ code. Now let's assume one of these components has a problem. By way of example, let's say there is a bug in this third-party library that you have no control over, or there is a bug in a driver which accesses some custom hardware. In this case, these components will be terminated. They can be restarted if possible, and then the system operation resumes. And while all this is happening, the rest of the system remains operational. And this is great for enhancing the reliability and the availability of the system. And guess what? We have, of course, mapped these functions to the QNX OS primitives of processes. Right, after this use case scenario, I just want to talk a little bit about the services that we offer. So there is a lot of low-level board support packages and driver development that we do. We do a lot of middleware solutions around Flex Control, third-party software, porting, etc. We also do design and architecture consulting, in particular in scenarios with heterogeneous environments. And of course, we have support and maintenance contracts at various service levels. And also we have licensed retail business for selected products in certain jurisdictions. Unfortunately, we can't do everything on our own. So also we have good and strong partners. So for the SOM hardware, of course, it's Phytec using the call. Likewise, for real-time OS, we are focusing very much on the QNX. For EtherCAT, we are working with Acontis. And if it is about data management, which goes beyond what Flex Control offers, we have a good relationship with ETIA. They specialize in real-time embedded data management. For industrial communications, we are working with Hilscher. And we also have a good relationship to OPC Foundation because we believe that this standard is very good because it combines both transport and data modeling at the same time. And we believe this is going to be more interesting in the future. Now to just resume, we have shown you in this webinar that building trust in embedded systems is a lot easier if you have good partners at your side that bring with them expertise in their field. We from BitCtrl, Phytec, and QNX have established a long-standing relationship of many years, and that enables us to tackle the most demanding projects together with you. So we invite you to benefit from our joint experience in the field of hardware, operating system, and system integration with Phytec, BlackBerry QNX, and BitCtrl. If you want to get in touch with us, at this last slide, you have all the contact details. And now we are very happy to take your questions. Thank you very much for listening to our presentation. And we are now going to the Q&A session.